Welcome to Lesson 14A, Example Problem, Supersonic Flat Plate Wing. In this lesson, I'll do a simplified diamond airfoil example problem. And if you think about it, the simplest possible diamond airfoil would be one of zero thickness, which would just be a flat plate. So I'll do the calculations for a flat plate at various angles of attack and calculate lift and drag. Actually, lift and drag coefficients. Here's the problem setup. We have a 2D wing that's simply a flat plate of chord length C, and we'll let S be the span into the page. We'll set alpha, the angle of attack, to 15 degrees first, and then I'll vary alpha to see what happens. Note that we'll get both a drag and a lift force on this airfoil. I give M1 2.6, the pressure and temperature in this region, and we'll start with alpha of 15 degrees. The lift and drag coefficients are shown where SC is the planform area, the area looking from the top when this airfoil is at zero angle of attack. So it's just the chord length times the span dimension into the page. And we define the planform area for the lift and drag the same way. Again, part A is at one given angle of attack, and then I'll plot CL and CD versus angle of attack in part B. Here's our standard assumptions and approximations: ideal gas, steady, isentropic, except across the shocks, of course, adiabatic. We'll assume that our oblique shocks are weak, so we still have supersonic flow downstream of the oblique shocks. The first thing I'll do is calculate the speed of sound from A equals square root of gamma RT, and I'll do this at region 1. We know gamma for air and R for air, and we plug in T1 to get our speed of sound. From this we can calculate the speed V1, and for the given M1 and using this value of A1, I get 832.2 meters per second. I also will need the density, so rho 1 is P1 over RT1, and plugging in our values, I get 1.1615 kilogram per meter cubed. And as always, I'll give my final answers to 3 digits, but I'll keep several more digits here to avoid round-off error. We expect the flow to look something like this. From region 1 to 2, we'll have an expansion fan here, but on the bottom, we'll have an oblique shock. The pressure is the same top and bottom at 1, of course, but pressure goes down through the expansion fan, and pressure goes up across the oblique shock. So we expect this force at the bottom to be larger than this force, giving us both a drag and a lift. Let's look at the oblique shock first. From 1 to 4, we use our equations for oblique shocks at the given value of M1 of 2.60, and we'll set theta equal alpha equal 15 degrees, which is the turning angle, and we can set those equal because we're neglecting the boundary layer and displacement effects along the wall. We use our theta beta m equation to get beta. It turns out to be 35.81 degrees. And we use our other oblique shock equations to get the normal component of M1, M1n, as 1.521, and then we use our normal shock equations for M4n across the shock, and this is subsonic, of course, since for the normal Mach numbers we're going across a normal shock from supersonic to subsonic. But knowing the angles, the actual M4 turns out to be 1.953, and I'm not going through all the details here because we've done oblique shocks previously. We're using the same equations. Then also from our normal components of Mach number, we get the ratio of pressures, P4 over P1. We get 2.533. From this, we can calculate P4 using ratios. So our ratio 2.533 we just calculated, and P1 was given. So I get a very large P4 acting on the bottom of the plate. Now let's look at the expansion fan from 1 to 2, where we also know how to calculate properties across an expansion fan. So again, I won't go into all the details. but starting at m1 equal 2.60, with again theta equal alpha equal 15 degrees, we use our Prandtl-Meyer expansion fan equation to get nu of m1, the Prandtl-Meyer function. I get 41.415 degrees, from which nu at Mach number 2 is nu at Mach number 1 plus theta. So adding 15 degrees to this number gives us 56.415 degrees. Now we have to solve implicitly to get m2 from the Prandtl-Meyer equation. I get 3.370. Again, you can do this any way you want. I'll show this in the compressible aerodynamics calculator, where I still have my values from our previous example, but here we want to enter the Prandtl-Meyer angle, which is already selected. Gamma is already 1.4 for air, and here I'll enter 56.415 degrees and hit calculate. You can see that the Mach number is 3.370, as I found here on my own using software. So we see the agreement, which always makes me happy. Now we use our ratios wisely. P2 is P2 over P1 times P1, but since this is isentropic flow, we can write P2 over P0, P0 over P1 times P1, where P0 2 and P0 1 are the same, since P0 does not change when the flow is isentropic. The first one, the ratio P2 over P0, is given here, and then similarly for P0 over P1, we have the same term in parentheses except with m1, and the exponent does not have this negative sign. And finally times P1 from here. I'll show you my values here in case you want to check your math. If you do this problem on your own, P1 is known, and these two are shown here. My final answer for P2 to 4 digits is 26.77 kPa. Now we do a little trig for our plate at a known value of alpha. And now knowing pressures P2 and P4, the lift force and the drag force can be determined, namely F lift is F bottom minus F top cosine alpha, which is equal to P4 minus P2 times the area, which is span times chord times cosine alpha. Similarly, F drag is F bottom minus F top sine alpha, which is the difference in pressure times S times C times sine alpha. Finally, with these two forces, we can calculate the lift coefficient, which is F lift or FL divided by 1/2 ρ1 V1 squared SC, and plugging this into here and plugging in all the other numbers which we know, I get CL is 0.453 at alpha equal 15 degrees. CD is pretty similar, and plugging in the drag force that we had calculated, I get a drag coefficient of 0.121, again to 3 digits, and again at alpha equal 15 degrees.
But, Professor, don't you also have to calculate pressures P3 and P5 on your diagram?
Great question, Willie. Let me sketch this. Here's our plate, our expansion fan, our oblique shock from 1 to 2, and from 1 to 4. To calculate pressure 3, we would have to analyze flow across this oblique shock, and to get P5, we would go across an expansion fan at the bottom, where there will be some slipstream of unknown angle. This is where we have to iterate as we discussed previously. You pick some angle and you try to get the pressures to match across here. So you iterate until P3 equal P5 at some slip angle. This involves some work, and to answer your question, we don't need to calculate P3 or P5. We know they're equal, and we know there's a slipstream in that V3 and V5 are not equal. But these pressures do not affect anything on the plate. The only thing that matters is P4 and P2, so we've already calculated the lift and drag coefficients, and you're welcome to try this if you want, but it's not necessary to calculate the lift and drag.
Thank you, Professor.
You're welcome, Willie. Finally, since I did all this in Excel, I'll repeat for various values of alpha, the angle of attack. I plot here both CL and CD. and I'll make some comments here. First, it turns out that CL increases nearly linearly with alpha, but CD increases more slowly all the way to 20 degrees. And then finally, at some large value of alpha, the flow will separate because the expansion fan cannot keep expanding in real life where you have some viscous effects right at that leading edge, and you'll get some flow separation, which people in the airplane business call stall. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.